All right, great. Well, hi, everyone. Thank you so much for being with us today. Welcome to the 9th event in our series of virtual research showcases aimed at highlighting dairy research from various researchers across Canada. We're very excited to have you here with us today. If you would like to listen to this session in French, you have the option of clicking the interpretation globe at the bottom of your screen, clicking onto the French channel, and you'll be able to hear our interpreter live interpreting the session for us today. I would also like to remind everybody that we're hosting this session as a traditional Zoom meeting, which means you'll be able to turn your cameras on and off as well as your mute button. We ask that for best audio quality and listening experience that everybody stays muted for the session. But if you do have questions, please feel free to put those questions into the chat. You can direct those either to the group or to myself, Julia Saracini, or my colleague, Carly Wright as well. We will be taking questions towards the end of the session. If we don't have time towards the end of the session to verbally answer the questions, any of the questions submitted in the chat will be answered electronically over email by our researchers as well. If you need any assistance during the session, please feel free to contact any members of the ACER consulting team, which is the team that I am a member of, as well as my colleague Carly Wright or Aaron Winans in the chat. You can contact us at any time by direct messaging us through the chat function. I would now like to hand things over to the DFC team for a quick introduction and thank you from the Dairy Farmers of Canada as we begin with our featured speakers for today.
Thank you, Julia. So hello, everyone. My name is Amy Desilets. I'm Assistant Director Research at Dairy Farmers of Canada. I first want to thank you all for registering for today's webinar. This webinar series was launched by DFC last fall as part of our ongoing commitment to research communication and knowledge transfer. This series aims at showcasing the exciting work that is going on in dairy research across Canada. This initiative is possible thanks to the financial support of DFC, but also as our partners. And I would also want to thank Andrew, Rob, and Merrin, as well as all the other research team from across the country for their collaboration on this initiative. And of course to ACER Consulting for organizing these events. So without further ado, I'll turn the floor over back to you again, Julia. Thank you.
Thank you, Amy. I'd like to introduce our first of a series of speakers today, Andy. So Andrew is a scientist based in the Central Experimental Farm located in Ottawa, Ontario. He's also an adjunct faculty professor in geography and environmental studies at Carleton University. Andy is currently involved in a number of research projects relating to understanding water use efficiency and methane emissions for manure storage in dairy farming. So it's my pleasure to pass the floor over to Dr. Andrew VanderZaag.
Well, yeah, thanks for the introduction, and happy to speak first about the project that we've been working on for the last 5 years, focused on reducing the water footprint of milk in current and future climates. On to the next slide. There we go. So we know that a reliable supply of clean water is really essential for dairy farming. And we also know that the water footprint is an important metric for the sector for characterizing how much water is used per liter of milk produced and keeping track of how the sector is moving towards its sustainable development goals. And the International Dairy Federation has produced a guide to the water footprint for dairy farming. And it includes more than just the water that's directly used in the farm, although that is one important part of water consumption. Other key elements in the water footprint include the indirect water that's used in the production of things that are brought to the farm, like off-farm feed or electricity, as well as anything that's done that may decrease the quality of water, such as nutrient pollution, will increase the water footprint. So this is important context for what goes into the water footprint itself. And we have a sense that Canada has a lot of fresh water, but as this graphic from Environment Canada shows, that that water is not always available when and where it's needed. So this shows in orange and red those parts of the country where at times and in some years, more than 40% of water recharge is used for human uses. And agriculture is a part of that. So water scarcity can be an issue at times and in some places. And added on top of that is climate change. So we've seen on the whole, for all of Canada, the average temperature has increased by 1.4 degrees since 1950. And that's faster than the global average warming rate. But more of that warming has occurred in the winter and more in the north. So as far as it relates to dairy farming and the regions where dairy is practiced in Canada, how may climate change impact those regions and the heat stress that may occur there, or the water use that's occurring there? Those are some questions that we wanted to look at in this project. So with the context of that I've just talked about, that set up the project that we've done for the last 3 years, and it has 3 parts. The first part is focused on measuring and understanding the direct water use in barns, and I'll speak about that first. The second part is focused on the heat stress and climate conditions that occur in dairy regions and within dairy barns, and how that relates to water use in current and future climates. And I'll speak about that from a measurement point of view, and we'll also tie that in to work from Edith Charbonneau's group. And the third part is indirect water use from things like electricity use and leachate from bunker silos, which Rob and Merrin will speak about in the latter part of the presentations. So to the next slide, I'll start on to the first component of the project, which is the direct in-barn water use. And so in the project, we identified nine farms and we instrumented them. They were selected because of their the different regions where they're located. So we have extremes in terms of quite far north, quite far south, more dry conditions, more humid conditions, different ventilation systems, mechanical and natural ventilated systems, different milking systems. And so we instrumented each of these facilities with weather stations outside, as well as sensors inside the barn to measure the differences in temperature and humidity, and THI, which is a combined indicator of temperature and humidity into one value. And we instrumented the farms with water flow meters to be able to measure the water that's used for different purposes within each barn over the course of multiple years. And with that instrumentation, as we'll see on the next slide, we were able to partition how the water is used and characterize time series data like what's shown in the graph here, how water flows change from minute to minute, from hour to hour, day to day, and over longer periods of time. So we could aggregate that data to what we'll see on the next slide, which is seasonal summaries of how water flow changes throughout each hour of the day on the left, and how that changes from season to season as each different color of line shows. And then taking those types of numbers and aggregating them into monthly totals. And we can see on the right how the total water, which is the blue line, increases to a maximum in the summertime, driven mainly by increased water intake for drinking from the lactating cows, which is the dark gray, and from the replacement herd, portion of the herd, which is the light gray. So that's total liters per cow, or liters for the whole herd. And on the next slide, we can look at how that breaks down over the course of a year and how water is used for different purposes on different farms. Now, this is just 3 farms to kind of illustrate. On the left, we have a farm with 35 milking cows in a tie stall. On the middle, a free stall milking 150 cows with robots. And on the right, a free stall milking 400 cows in a parlor. And if you look at the donut graphs, you can see the blue indicates the percentage that's used for drinking. And that ranges from 68% on the right to 83% in the middle. And the amount of water in total over a whole year varies from 1.9 million liters on the left to 33 million liters on the right. And the trucks on the bottom give just a feeling of how much water that would be if it were delivered by trucks. So a truckload a week in the case of the smallest farm, 3 truckloads a day in the case of the largest farm. A couple of other points to note here. The cleaning water represents about 18% in the farm on the left. In the middle, we have a green piece that's 3% of the total, which is water used for a sprinkler system. And on the right, 15% represented in the orange is the amount of water that was used in a heat exchanger called a plate cooler, which was not recovered for any other use. And the numbers in the middle represent the amount of water per liter of milk, ranging from 5.3 up to 6.5. And on the next slide, I'll look in a little more detail into how much water is used in different milking systems. Now, this graph is what I'll focus on the right. And this represents all of the farm data from the current study, plus the data we gathered in a previous study, combined with data from another study done in Ontario by Harold House and colleagues. And that's 41 farms with different milking systems that's represented in this graph. So what we see from each group is the average water used per cow per day from a tie stall. Average is a little under 22 liters per cow per day. In a parlor system, around 26 liters per cow per day, up to 40 in robotic systems. But you can also see that the blue represents the variation around the mean. And the variation is larger for parlor systems and even larger for robotic. And another thing is, if we look at the farms that were below the average from each group, we can start to understand what some farms may be doing that may be conserving water for this purpose on their farms. So in the tie stall systems, one of the things is a conservation sink, which has the shape, a bit of a Y shape, which I've shown on the left. And that minimizes the amount of water required to submerge the milking assembly for washing. I'll talk more about parlors on the next slide. And for robotic systems, a couple of points to highlight is that the use of a brush instead of water for teat cleaning reduces the amount of water required, as well as changing the frequency of floor washing can reduce the amount of water for that system as well. On the next slide, we'll see what some farms were doing to reduce water use in their parlor system. And the first thing is to potentially scrape the holding area prior to washing it, or to use a pressure washer rather than a high volume hose. That may take longer, but it does use less water. Reusing water is also valuable. For instance, to reuse some of the rinse cycles for floor wash is something that some of the farms were doing. And just to walk through some numbers from one farm, just to put some numbers to it. So this farm has 200 milking cows. They're using, in the baseline scenario, 74,000 liters per day. 19,000 liters of that was for the plate cooler, that's the heat exchanger. If all of that water was recycled, reused for drinking, then that would reduce the total by 26%. And then the floor wash was 3,500 liters a day. And if that water was instead recuperated from recycling some of the rinse cycles from the milking system, then that would also be reducing the total by 6% down to less than 52,000 liters per day. Onto the next slide then. So in the earlier slide, I showed the average for robotic milking systems was higher than for parlors and tie stalls, but this is an example where we had a nice opportunity in the current study to measure water use at a farm that was initially using a parlor for 2 years, and then in the third year, they switched to using 2 robots. And what we found here with the measurements at this farm before and after was that the amount of water used for cleaning the milking system decreased by 9% when they switched to robots. Now, these robots were using brushes instead of water for teat cleaning, so that's a contributing factor. Also, if we take into account that with the robotic system, they're milking 2.8 times per day on average rather than twice, and producing more milk, then the savings is even greater when scaled per unit of milk production. On to the next slide. I wanted to also make the connection between the wash water use and manure storage capacity. So this is just an example farm with 120 cows and a manure storage there. So if their milking system was using 40 liters per cow per day, that would contribute 73, that would require 73 out of the 240 days of storage capacity. Whereas if their milking system was using 25 liters per cow per day, that would be about a month of additional storage capacity. And given how expensive it is to build a manure storage, in the interest of expanding a herd size, for example, without increasing storage capacity, this is something to consider. There's also the cost of moving manure and spreading it that goes up the more water there is. On to the next slide. Another thing I just wanted to touch on is that we saw at almost every farm was occasionally there would be water leaks. This could be something simple like a stuck float valve or a trough that wasn't level and was overflowing. And the important thing is just showing two contrasting examples. In the top, the graph shows a leak that was noticed within 24 hours and fixed. In that case, only 10,000 liters of water was leaked directly to the manure storage. In the bottom, it was a leak that went on for almost 2 weeks before it was fixed, and that contributed several 100,000 liters of water to the manure storage. So just having a procedure for keeping an eye on this, and the quicker these things can be noticed and fixed, then the better. On to the next slide. So taking all of that, those observations and putting them together into some benchmark numbers, what the table shows here is the total farm or barn water use in winter and summer, and then the drinking water in the winter and summer for the herd. And you can see the drinking water is 3.8 on average in the winter, 4.4 on average in the summer. The total for the barn is higher, 5.8 in the winter and 6.7 in the summer, averaging out to 6.3 liters per kilogram or liters per liter roughly. Now that excludes manure dilution water, which was water added specifically for making the manure more flowable and able to be pumped, which was done on a couple of farms, but not every farm. So that's an area where there could be some water conservation, but it wasn't applicable at every farm, so I didn't include it in the benchmarks here. Now to take those benchmarks and put them into a broader perspective on the next slide, if we consider that Canadian dairy farms produced over 9.5 billion liters of milk per year, with the number of 6.3 liters per liter, that would work out to around 60 billion liters of water per year, directly used in barns. And that's comparable, just for a reference point, to the 9th largest city in Canada. And there's some opportunities for reducing that number through some of the things I've just described. And if the sector could reduce the water use by 1%, which doesn't seem like a big percentage, that would add up to 600 million liters of water per year. So just to put some bigger context to it. And that wraps up the first section of the project about direct water use. So now I'm going to talk about the heat stress and climate change components and how those link to water consumption as well. So what these graphs are showing is they both have THI, the temperature humidity index, on the x-axis across the bottom. And on the left graph, we see the lying time. That's the amount of time that cows are spending lying down. And we can see that as the THI increased from 65 up to 78, the amount of time that the cows spent lying down decreased by about 2.5 hours. So that's 2.5 extra hours of standing up, less energy available for milk production. And then indeed, on the right, we see the amount of water per kilogram of milk produced. That increases at every farm as THI increases. And in some cases, the increase is as much as 40%. So more water per unit of milk. So how does that maybe, what's the context in terms of climate change in the past and future, and how that may link to water? Let's look at the next slide. First, we looked at the historical data. This is measured temperature and humidity from weather stations in different parts of Canada. The map here shows the circles, which are the weather station locations, and the green and red and yellow indicate the number of dairy cows in that region, red being the highest. And what we noticed, or what we determined from this very large data set, was that in the prairies from 1960 to 2019, there was a significant increase in humidity but not temperature or THI. But in BC and Ontario and East, we've seen a significant increase in temperature and THI at all stations. So just to give an example of what that looks like, the graph on the right shows London, Ontario, and you can see the increase in temperature from the 1960s to 2019 by about 1.5 degrees during the warm season, so from April to October. And THI over the same period increased by 2 units. So that's historical measured data. And if we go to the next slide, we'll see what climate change projections, how they can give us a sense of what the future may hold. So we've looked at 5 global climate change models and taken the average of those models. And each model uses different future scenarios, which takes into account whether greenhouse gas emissions increase at slow, medium, or high rates. And with that data, we can look at maps like what I've shown on the right, which indicates warming and increased THI load in most parts of the country, less so in Newfoundland and Alberta. But for most locations, this means more warm days, fewer cool nights, more days above THI thresholds, and longer sustained periods of heat, like heat waves. So the data in the table show an example of London again, where you can see each indicator increases by at least double into the future under a moderate warming scenario. And on the next slide, we'll see that the cows are not outside in most cases. And the data that I've shown up to now was for outside conditions. Now we've looked at, in our current study, what are the conditions inside barns compared to outside? And each of these graphs relates the outdoor THI on the x-axis to the indoor THI on the y-axis. So if the data are to the left and above the diagonal line, it means the inside conditions are hotter or have a higher THI than outdoors. So with both mechanical and natural ventilation systems, we see the indoor conditions are higher than outdoors. With mechanical ventilation, when the ventilation is running, which is typically when it feels hotter, then the indoor conditions are quite close to the outdoor, but as it cools down, there's a tendency to turn off or slow down the fans, and that means the indoor conditions get hotter than outside. So there'd be a benefit to having more ventilation, especially in the evening and overnight when it's cool outside. Bring that cool air in and decrease the THI indoors. On the naturally ventilated systems on the bottom, just go back for a sec. Yeah, thanks. The naturally ventilated ones on the bottom, they're more consistently higher. And that's partly the issue, is that there just isn't enough wind, especially at night and the evenings, to bring in that fresh air from outside and move the warmer, more humid air outside. So that's an issue that's still outstanding. Onto the next slide, shows another area where increased ventilation can be beneficial, which is in milking parlors in the holding area. The data in the graphs, if you look at the dotted blue line, that's the THI in the barn. If you look at the black line, that's the THI in the holding area. And the increase in the black line over the blue line is when milking is happening. So you can see the farm on the left. During milking, there's an increase of THI in the milking parlor holding area when in the afternoon, but it's only by about 1 unit higher than what was in the barn. And that's because that facility has open curtains on both sides, enabling a nice breeze or more ventilation to occur. Whereas on the right, we see a much larger increase in the holding area. And that's occurring at the peak in the middle of the afternoon. So the THI is approaching 74. And if you look at the design there, there isn't an opening on the left side to enable air to blow through. Moving on to the next slide. The final point here is just about the use of sprinklers, which was used on one of the farms to cool the cows in the summertime on warm days. The sprinklers themselves use up to 60 liters of water per cow per day. They do decrease the amount of increase in the water use, or they stabilize the amount of drinking water that cows are drinking during the summer, which is good. But overall, it increases the amount of water demand and the peak water demand in the summer because of the amount of water the sprinklers are using. And that wraps up my portion of the presentation. And if we go to the next slide, I'll now present some work from Dr. Edith Charbonneau and her team and the Department of Animal Sciences at the University of Laval. Unfortunately, Edith's not able to present today, so I'll present on her behalf. And this work is about evaluating heat stress in dairy cows and mitigation options for current and future climate scenarios. It's a modeling-based approach, and the models I'll be describing on the next slide. The information for the models is gathered from, sorry, I can go back for a second. The information for the models was gathered from different provincial sources, and there's climate change component, which is based on the simulations that I described already. There's 3 periods that you'll see on each of the graphs. The green represents the reference period from the 1980s to 2015. Then in the middle of each graph, the middle section, that's the near future from 2040 to 2069. And then on the right of each graph is the long range future climate scenario, which goes from 2070 to 2099. And in each of those future scenarios, there's either a moderate in blue, intermediate in yellow, or intense in red warming scenario. So you can see here in the graph the increase in the number of days above a THI threshold as the different future scenarios unfold and into each of the 4 locations. In addition to that, there's 2 farm ventilation or cooling scenarios that are addressed. One is with the current existing ventilation systems, either natural or mechanical or tunnel. And then the addition of a misting system with high-speed fans as a cooling measure. So if you go to the next slide now, you can see more details about the 4 typical farms that were modeled, and these are based on those provincial data sources to describe a typical farm in each of these locations, again with contrasting regional climates and management. And the 2 models that are driving this, the first is called N cycles. It's a whole farm model that models everything from the cow's milk production, the whole herd dynamics, the feed required, and the production of that feed, and the economics associated with it. It's an optimization model, so it can maximize net revenue under a set of parameters. And in association with that is a crop model called STIX, which is driven by daily weather data and management practices. And so that enables a simulation of the crop production under different climate change scenarios that provides the crops for the whole farm model for the feed production. A couple of other points is that the in-barn temperature and THI conditions were based on the equations that I showed earlier. And changes in milk production, milk protein, and fat were based on recent data from a Canadian study as well. So we can move on to the next slide as well to look at some of the results. This graph shows projected decreases in milk solids, so decreases in fat and protein production as a result of heat stress. And you can see all the numbers above each of the bars are negative, which indicates a loss, a financial loss because of the current and future heat stress conditions. And in the future heat stress scenario, the future climate scenarios, the negative values get larger, up to $190 per cow per year in the distant future under intense warming scenario. There's also differences between locations, with Ottawa having the highest losses because of the warmer climate. In the next slide, you'll see the same analysis, but in this case, with a misting system added. And the bottom line here is that the installation of this system reduces the amount of loss by 30 and 35% for milk fat and milk protein production. So the negative values get smaller, which is good. And the mitigation effect, though, is less effective in the more humid locations because the benefit of adding water for cooling is less when it's already a more humid location. On to the next slide. So now the model was used to connect the production and the water footprint under those different climate scenarios. And I want to highlight that this incorporates the same direct water uses that I was talking about earlier, but in addition to that, some indirect numbers specifically about feed production including on-farm feed and imported feed, including the energy associated with fertilizer production, seeds, and other inputs, as well as irrigation, which was relevant for some of the purchased hay in Red Deer. And moving on then, we'll look at some of the results from that analysis on the next slide. So this shows the water footprint results for the 4 locations with the current ventilation system. In the top left is the water footprint for Halifax, and each of these graphs has a lot of numbers in it, so I'll just walk through the green bar in the reference scenario for the top left graph first. So at the bottom is 5.7, which is the amount of water associated with feed production. Above that, 4.0 is the amount of water associated with drinking water in the barn, and then other water uses in the barn is above that. And in total, you get something around 14 liters of water per kilogram of fat and protein corrected milk. And you can see as you move to the future scenarios that the total increases slightly or more so in the distant future under the intense warming scenario. For Halifax, Quebec, and Ottawa, the results are fairly similar, but for Red Deer, there is an important distinction, which is that the amount of water associated with feed production is much higher than the rest, and that's because of some of that imported feed that was irrigated. But what changes in the future and the distant future is the amount of yield that's produced from the locally grown feed. And the models suggest that in the future, with the additional growing season and heat units, that the yields would be higher for the locally grown feed, so less imported feed would be required. Therefore, the water footprint associated with feed production would decrease in that scenario. Moving on to the next slide, you can just summarize those main findings. That first, the bullet shows just the average values for the water footprint in the reference period. And the second bullet, or the third bullet, shows that drinking water increases by 10% for the long-range future under the intense scenario. So we do see a tendency towards increased drinking water demand owing to the warming conditions. And that's after the feed intake has already been optimized to reduce crude protein and salt intake to reduce the drinking water. So another big impact was on feed production. So with better yields, the same inputs reduce the water footprint in the future. But there is some risk of drought stress according to the STIX model in the future in some locations. Moving on then to the next slide, we can see the water footprint with the misting system in this case. So that's the same bar graph, but in the very top is now a number 0.1 in the top left corner, which is the water use for the misting system. And that increases up to 0.3 or 0.4 in the future with more warming and more demand on that misting system. That is offset partly by a decrease in a moderation of the increase of drinking water though. And if we go to the next slide, there's a summary of the water used with the misting system and the high-speed fans. We see that drinking water is reduced by 1%, but there's an increase in the water used for the misting system itself. And there's a change in an increase in the amount of electricity used. Overall, even though the milk production is more stable and higher, there's an increase in the average water footprint compared to the current ventilation system because of the water used for the misting system. And onto the next slide, we get a summary of some of the financial considerations. The graph through locations, Quebec and Red Deer, and it's the economic impact, which includes some positive numbers and some negative numbers in the bar, which is some changes in the revenue and costs. And in summary, there's climate change is projected to have an effect on the crop production, generally an increase in yield in most scenarios. The addition of a misting system is projected to increase costs by around $34 per cow per year. And overall, that results in a reduction of the net revenue for the farm of about 3%. So 2 final thoughts then. The first is that the existing ventilation system should be optimized before considering the use of misting. And secondly, that cooling strategies should prioritize cow comfort, potentially over farm profit. And that concludes Edith's presentation, and now we'll pass it to Rob. Thanks.
Thanks, Andy. I just want to also thank everybody who's already submitted questions in the chat. As a reminder, if you have any questions for the presenters, please submit those to the chat. You can send them directly to myself or to my colleague, Carly Wright. I now have the pleasure of introducing our next speaker, who is Dr. Robert Gordon. So Rob has served in a number of leadership roles, including being the former Dean of the Ontario Agricultural College at the University of Guelph, Dean of Research at the Nova Scotia Agricultural College, and Canada Research Chair in Environmental Resource Management. He has maintained a strong research profile, supervising more than 60 graduate students and postdoc fellows, and published more than 160 peer-reviewed journal articles. So with that, I'd like to turn it over to Rob.
Okay, well, thank you, everybody, and it's really great to be here as well. I'll try to be brief with my comments. A couple key simple messages, certainly, in this kind of consideration around energy use on dairy farms and water is that really it's important to recognize that the farm energy grid mix can really influence the overall water footprint, and also that energy conservation on dairy farms can also reduce the water footprint as well too. So I'll spend a few minutes talking about some of our work related to that. Next slide, please. As you're all well aware, certainly energy is an essential source of electricity is an essential source of energy on dairy farms. Really recognizing as well too that the source can have either low or higher carbon emissions depending on where that source emanates from. As you're all well aware, Dairy Farmers of Canada made a commitment in 2022 to become net zero by the year 2050, with some significant milestones that they've identified over the next 6 or 7 years as well too. I think it's also important for us to recognize as we build up approaches around energy conservation on farms that there's a significant amount of new technology that will assist with this. And certainly, as you're all well aware, over the past 20 to 25 years, there's been strong efforts through environmental farm planning to really enhance energy conservation. And so I think certainly some of the new things that we're looking at will provide a framework for doing that more effectively moving forward. It's important for us to recognize, too, next slide, that electricity also has water impacts as well. Certainly we've been doing a little bit of work looking at this and identifying its context with respect to dairy farming specifically. So we recognize that certainly, you know, the source of energy production in many cases will have either significant consumptive water considerations, or even in many cases too, non-consumptive water use considerations that have to be built into the overall water footprint of that end use, and in particular, certainly in terms of milk production as well. So we've been spending quite a bit of time trying to really build in a framework to really better understand, depending on the location of the farm, within which province, what that overall energy-based water footprint could include. And so we'll walk through a few examples of what this kind of represents in many ways to help us moving forward with respect to looking at energy conservation, but also the water footprint of dairy production systems. When we're looking at, next slide, please. When we're looking at water impacts, again, as I've said already, there's certainly consumptive, but also non-consumptive water use considerations. When you're looking at from a consumptive perspective, hydroelectric power generation has the highest water use. Certainly a real important opportunity around the use of renewables on dairy farms, in particular wind and solar, have very, very low water footprints as part of their production as well. It's important to recognize too, from this graph, as you can see, hydro has the largest. Some of the other typical energy production systems, gas and oil, coal, nuclear, have modest consumptive water use considerations, but their non-consumptive water uses are about 25 to 35 times higher than consumptive considerations as well. So if you look at the role that all of these different sources of energy production have in the water footprint, they are pretty significant. As we've talked about already, every province has a slightly different grid mix that it deals with. Certainly Manitoba and Quebec are mainly hydro-based provinces. Ontario is largely hydro and nuclear. Alberta, Nova Scotia are coal and gas and oil. And PEI certainly has a high proportion of its energy grid mix coming through wind turbines as well. So that all influences, as we'll talk about, the overall considerations around how you can conserve energy, but also what the overall water footprint benefit would be. So we've done quite a bit of work, next slide, in terms of trying to better understand some of these key considerations. And we published a paper back in 2021, and it was really a review of dairy farm electricity use, conservation approaches, and renewable production opportunities on a global perspective. And we actually looked at, we summarized over 35 studies from Canada and internationally, where we, I think, framed a number of key rules of thumb in terms of electricity use indicators on dairy farms. And certainly we found on average that electricity use indicators are around 9 kilowatt hours per 100 grams of 100 kgs of milk production. And also a typical cow represents about 1,000 kilowatt hours of cow per cow per year in terms of its electricity use. It's important to recognize that depending on the dairy production system, for example, pasture-based production systems have an incrementally lower energy use associated with them. But certainly we've been doing a lot of work to really characterize what these energy considerations are and how we can find ways of enhancing their conservation approaches, and then from that, reducing the overall water footprint of those production systems as well. Next slide. So in terms of the water impact of electricity use, as Andy mentioned early on in his presentation, and if you do a pretty extensive review, you'll find that on average, the water footprint within the dairy barn itself represents around 7 liters of water per liter of milk produced. And certainly it's also important for us to recognize the source production of electricity, as we've been talking about, represents around 2 liters of water per liter of milk to produce that energy as well. And there's really a significant opportunity through conservation technologies, but also the use of renewables to reduce this component of the water footprint as close to zero as possible. So a way to think about it is that energy production represents about 22% of the overall water footprint of the dairy production system as a whole, which is around 9 liters of milk, 9 liters of water required to produce 1 liter of milk. Next slide. If you're looking again, we've done an extensive amount of work in that review article to look at the various uses on dairy farms of energy. And certainly it's important to recognize that about 30 to 50% of the energy in confined dairy production systems emanates from milk cooling and water heating, but there's certainly also a number of other electricity uses, including lighting, fans and ventilation systems, water heating, as well as manure handling considerations as well. And so we've taken an approach to say, what are the opportunities in front of us to be able to mitigate some of these, and conserve more effectively electricity use within dairy production systems, with the ultimate goal of reducing the water footprint. Next slide, please. So in terms of conserving electricity, certainly a lot of research done in terms of what lighting can provide. LED lights, for example, use approximately 50 to 90% less electricity than metal halide, fluorescent, and incandescent lights. And again, certainly there's been studies that have demonstrated that with a significant lighting period of 16 to 18 hours per day, you can also increase milk production. A lot of work done too on use of variable speed and variable frequency drives on on fans, on vacuum pumps within production systems, and certainly the payback for these is shorter when you're using higher horsepower and longer runtime applications with those systems as well too. Next slide. Certainly in terms of conserving electricity, a lot of work done on identifying ways at which we can support a more effective energy use in terms of cooling and heating systems, certainly in terms of pre-cooling milk with heat exchangers or plate coolers is certainly one option. And we have found that that could certainly provide a 40% reduction in energy use. And then there's also the opportunity of reusing that for drinking water, and also certainly using tankless water heating as another option, and also using cold wash water approaches with respect to milk hose pipeline cleaning as well too. So various approaches that can be used in barn for reducing energy use as well. So if you look at all of these different new technologies and approaches that we can use within dairy production systems, we've done a little bit of work to demonstrate that if you look at them systematically, there's an opportunity through using these new technologies to reduce your overall energy use by about 30%. And so the table here really represents a hypothetical 100-cow dairy herd where without these energy savings, the typical use would be around 250,000 kilowatt hours per year. And then by using the new technologies that I've spoke about, heat exchangers, tankless water heaters, LED lighting, VSDs as well, you could reduce that annual energy output to 178,000 kilowatt hours per year as well. So significant savings there. As we've talked about already, next slide, certainly the use of on-farm renewable systems really will help to increase the overall or decrease the overall water footprint. Both solar and wind have a zero water footprint associated with their implementation. So encouraging ways for us to really implement more use of renewables on farm, and then using those as a way to reduce that overall grid mix of other energy sources will go a significant way of reducing that 2 liters of water per liter of milk as part of the energy use component of the overall water footprint. Next slide. So really in summary, as we've talked about a number of key things, electricity can be certainly a low carbon energy source on farm, but generating electricity also requires water. And certainly I think it's important for us to recognize that's an important overall consideration of the water footprint. As we've talked about, it represents up to about 2 liters of water per liter of milk for electricity production, but ways at which we can reduce it substantially is through the use of on-farm electricity conservation measures and also using more effective renewables, including solar and wind. So on that note, thank you for your time, and I will pass it over to Merrin next.
Thanks, Rob. Thanks, Rob.
Oh, sorry, Merrin. I was just going to do a quick introduction to you, if you don't mind. So this is Dr. Merrin Macrae. She's going to be sharing some results of her research as well, and her research interests center around the effects of changing hydrologic conditions on biochemical processes in both natural and disturbed environments. And her work largely involves both field as well as laboratory research, study areas including sites across Ontario, Quebec, Alberta, as well as Manitoba. So thank you so much, Merrin, and the floor is yours.
Great, thank you. Bonjour, it's a pleasure to be here. Yeah, so today I'm going to talk about the potential contribution of bunker silo effluent to water quality issues. If you could advance to the next slide, please. Okay, so bunker silos are not necessarily something that might come to mind at the very beginning when we start to think about dairy farming and water quality issues. Other things might come to mind first, such as manure management. But the reality is that certainly bunker silos are one thing that many are using in the landscape that can actually be providing nutrients through nutrients to waterways. So when we start to look at these things, we don't necessarily think that there's a lot of leakage going on, but if you can see from the photographs on screen, there's not a lot of volume to this material, but you can just see these little trickles that might emerge when these things are filled. And this actually, even though it's low volume, can be quite significant. If you could advance the next slide, please. So the total volume of leakage, like I said, can seem very small, but it actually is very concentrated material. And so if you can see on screen, there's a lot of concrete damage, for example. This is very low pH, high biochemical oxygen demand, and noticing if particularly phosphorus, if you can see on the screen, the concentrations of dissolved reactive phosphorus in this material are very, very high, much, much higher than obviously what we want to see in our waterways. If you could advance to the next slide, please. So one problem is how to actually quantify this material. Like I mentioned, it's very low volume material, so it's really hard to measure. Oftentimes when we want to measure the loads or yields of material in the environment, we will measure the volume of flow and the concentration of that material. But because it is so low volume, it's really hard to capture it. So what we did as an approach is we measured concentrations above and below a bunker silo. And so you can see in the picture in the map on the screen, the location of the bunker silo. And you can see that it's certainly not discharging directly into a river or a stream. There is certainly a riparian wetland that is being used to treat the material, and the farmer actively harvests that material. So the idea is that it's going to intercept and treat some of this material. So what we did is over about a 1-year period, we measured concentrations in the stream upstream and downstream of this bunker silo. If you could advance, please. Okay, and so there's 2 graphs that you can see. The one on the left, what we did first is we're just comparing concentrations of soluble reactive phosphorus. So that's the bioavailable fraction that we're quite concerned about, because that, of course, is the fraction that is available to algae that would basically, algal growth. So we looked at concentrations above or upstream and downstream from the bunker silo. And we looked at it from January till about July, which is when, which is basically the pre-fill period. And then we looked at it again after the annual filling of the bunker silo. So that's the red symbols, that's the post-fill period. And the other thing, if you can see on screen, that I actually sized the symbols on the graph on the left with regards to how much water flow or discharge there was. So do we see accelerated concentrations downstream of the bunker silo associated with peak flow or flushing conditions? And so yes, there is some evidence of that, but the really significant losses, especially as far as total phosphorus goes, but really in both cases happened after the annual filling of the bunker silo. And you can see, especially if you look at the graph on the right, on the bottom, you can really see the divergence between the blue and the red. So essentially what we're seeing cumulative losses of both flow and then losses of SRP and TP. And so what we can see is that really on an annual basis, about 30%, 32% of the dissolved reactive phosphorus and 22% of the total phosphorus losses from about a 15 square kilometer watershed came from a single bunker silo. If you could advance to the next slide, please. So I think it's important to note that, like I mentioned earlier, this farmer is not discharging directly to a stream. There is a treatment wetland that is in place. So what we looked at is we tried to look at the efficacy of these wetlands at retaining phosphorus. And so we compared 2 systems. One was just a natural buffer strip, such as the one that was used in the first study. And the second is one where they had a constructed system that was quite a bit more elaborate, where there was actually a swale as well as a slag filter in the middle of that wetland. If you could advance to the next slide, please. And so you can see the graphs on screen, or the maps on screen. So you can see the bunker silo, and you can see the runoff from the silo through the riparian zone and into the stream in the top. And the red arrows are actually showing you sort of the predominant concentrated flow paths where the trickles were going. And then you can see at the other site, with the constructed site, you can see where the bunker silo is. And then you can see we've highlighted the pink areas, or areas that are really directly receiving this material. The bluer areas are where you, under more at higher flow periods, you might get some overflow, or they're indirect because they're just not quite directly in the line. And then the green areas tend to be unimpacted. They're more indicative of what might be naturally there. And the picture on the right-hand side of the screen is actually showing you what the slag filter looks like at the second site. If you could, and the blue arrows you can see are the direction of flow. So if you could advance to the next slide, please. And so what we did is we went out and so we sampled the soils throughout these different zones, as well as some of the pore water and surface water, to just get a feel for whether or not concentrations differed. Phosphorus concentrations differed between these very heavily impacted sites and these areas that were more indirectly impacted, and also those that were unimpacted, so basically more natural or quasi-natural systems. And if you could advance to the next slide, please. And so what we actually found is that wetland areas that, and so again, this is showing you in pink, that directly received the effluent had very high soil phosphorus. And so the graphs, the panels on the left and the left and the middle of the graph on the right-hand side of your screen are showing you the soil water extractable phosphorus and total phosphorus also with depth, and it's showing you differences between these zones. And then the panel on the absolute right, so that would be C and F, they're also showing you the phosphorus sorption index, and they're just basically telling you how close to being saturated are those sites. So a low PSI means that it's nearly saturated, either nearly or is saturated, and a very high PSI means it can hold on to a lot more phosphorus. And so what we can see is definitely those highly impacted, directly impacted sites that were in the direct line of that flow were quite high in phosphorus, and they had a very low sort PSI, meaning that they really couldn't take on anymore. And we were starting to see increases in the blue zones. But then in those, on the other hand, in those more natural areas, they of course had a lot lower phosphorus concentrations and had a much higher phosphorus sorption index. So essentially, and the other thing that's interesting in the bottom one is you can see the slag, and it is just so that you can see it, it's scaled. So you have to multiply it by 2 to get the true PSI. So the slag had a lot more potential for absorbing phosphorus or removing it from runoff. So what this is showing us is that, yes, soils receiving bunker silo effluent in these wetlands are very high in phosphorus, and really not necessarily in those directly respond, the pink areas that are directly receiving it really are saturated and can't take on any more phosphorus. And so anything that they receive is just going to pass right through them. And the slag filter is showing us, in fact, that that really has made a considerable difference at reducing the phosphorus, and it can retain a lot more. If you could advance to the next slide. So the fact is that these are similarly sized farms. They have a similar amount of animals, and so we really expect the volumes of bunker silo effluent to be very similar between these sites. But the riparian site, really, it's probably not been, it's about 20 years old, and it is very close to saturation, and it's probably not retaining anything. If anything at all, it's very little. The constructed site, on the other hand, just the wetland itself, the soil probably has at least another 3 years of retention before the soil will saturate. But with the slag filter, it's about 5 years old, so it's probably got at least another 5 years before it will also saturate. So what's important to remember is that, yes, people are putting treatment systems in, and some of them are more elaborate, and they are much more effective at retaining this material, but even any of these systems are going to have a life expectancy, and they're going to need maintenance and refreshing over time to make sure that they continue to retain this material. Next slide, please. So the takeaways, the problem is that this effluent is highly concentrated materials, and we really want to avoid locating them away from waterways. And the effluent that is discharged from them really needs to be treated. Wetlands, just putting a vegetated buffer strip in the way isn't going to work because they rapidly become phosphorus saturated in a matter of just a few, several years, like probably 5. And if we can construct systems with phosphorus sorbing materials, things like slag or other things, that can make a very big difference. The problem is how to make this happen. So part of it is it's just not simple to effectively design and install these systems. We want to make sure they're being done so that they're going to be effective. They're not going to clog up. The other feature that's an issue is the acquisition of phosphorus sorbing materials. You can't just go and get slag and pour it in the ground. They won't just sell it to anyone. So we need to put mechanisms in place where we can work with people to put these systems in place so that they can effectively treat things. And so obviously it's getting the materials, it's the design, but even funding or cost sharing to help people manage this. But I really think that treating bunker silo effluent is very much low-hanging fruit in that we could really make a big difference for phosphorus losses in some of these landscapes if we can do something about the bunker silo effluent. And with that, I thank you for your time today.
Thanks, Merrin. Thanks so much to all of our speakers today, Andy and Rob as well. It's been a pleasure to learn more about your research. Thank you to everyone who attended today. It's been great to have you. And thanks to all for who have submitted questions in the chat. Please stay tuned for the promotions coming up about our next virtual research showcase that will be happening in about mid-April. So keep your eyes peeled for some promotions coming from our team. And with that, thank you all for coming, and we're looking forward to seeing you next time.